Hello everybody, this is Mrs. Logus and I'll be taking you through cumulative review packet number 6. So let's start here with number 1. And numbers 1 to 3 ask about find each limit as x approaches infinity or negative infinity. And as you might remember from the last unit, a limit is really what a graph is getting really close to. And so another way to think of that is a type of asymptote. And we talked about 3 types, for end behavior asymptotes, we really talked about either a horizontal asymptote or a slant. And so when you're really finding a limit to infinity, you're really thinking about where the graph is approaching, which is the same as an asymptote. So if we looked at number 1, as x is approaching infinity, notice that we have a bottom-heavy function here. And so whenever you have a function that's bottom heavy, what you're really doing is taking a small number, for instance, like a small number like 1, and you're dividing that by a very large number like infinity. If you take 1 divided by infinity, that is very close to 0, so the limit must be 0, or the asymptote that I'm approaching will be a horizontal one at 0. Number 2 is not a rational function. We don't have a fraction, so we can't think of it as top heavy, bottom heavy, or neither. But we could either plug things in algebraically, like negative infinity to the 4th minus 6 times negative infinity, or we could think of it algebraically. From earlier units, you might remember that an x to the 4th function is even, and because it's a positive number in front, the function would look something like this. So as the graph, or as the x values go towards negative infinity, the y values are going to go up towards positive infinity. So I'm guessing my answer is positive infinity for 2 from the graph. But if I want to make sure from a algebraic perspective, negative infinity to the 4th or any number that's negative to the 4th is a positive number, and then negative times negative is plus 6 times infinity. So you're really doing infinity plus infinity, which would get me the same answer as if I looked at it from a graph. Number 3, if I'm looking at as x approaches negative infinity, I look at my first 2 terms and I notice that it is an even heavy function. Whenever it's even, I just take the 2 coefficients and compare them. So I would compare 6 is to 15. So my limit or my asymptote, my horizontal one that I would be getting really close to, reduced, if I divided these both by 3, would be 2/5. The next example for number 4, it asks you to graph the rational function and finding all this information about it. So the first thing we want to find or determine is what kind of asymptote that we have, and that's related to numbers 1 to 3. I notice that if I look at my first 2 terms, I have a top-heavy function, which means that I have a slant asymptote. And if I have a slant, that means I do not automatically have a horizontal line I can't cross. So if I wanted to find my slant asymptote, I would take x squared plus 3x and divide that into x cubed minus 2x squared minus 24x. Unfortunately, this bottom part of the rational function is squared, so I cannot do synthetic division. You can only do that if this is linear. So let's do some long division. X squared goes in x cubed x times, so I'm going to put that above its like term. Multiply that back, you'd get x cubed plus 3x squared. When you're doing long division, you would change the signs on both, so these would cross out, and you would get negative 2 combined with a negative 3x squared, so you would get 5x squared minus 24x. X squared goes into negative 5x squared, negative 5 times. Then if I multiply that back, I would get negative 5x squared minus 15x. I would change the signs because I'm subtracting. So I would have, that is a negative 5, so that would be a negative 19x. I'm actually done here though, because at this point the negative 19 is a remainder. So my slant is just the x minus 5, or even better, y equals x minus 5 would be my slant asymptote. My domain is found after factoring and before I cross anything out. So if you wouldn't mind, if I do the function down here just to save a little room, if I look at the top of this function, if I take out a GCF of x, I'd be left with x squared minus 2x minus 24 in the numerator, and the denominator I would have also a GCF of x, and I would be left with x plus 3. If I look at my denominator, I will keep factoring this in a little bit, but if I look at my denominator, I already know that my domain is everything I can't cross in the denominator. So from here, I know that x cannot be 0 or negative 3. So my domain would be from negative infinity to negative 3, union, negative 3 to 0, and then 0 to infinity. Now let me keep factoring this. Keep factoring that quadratic there. That would be x minus 6, x plus 4, over x times x plus 3. I noticed that once I factored everything, that these x's cross out, so that would become a whole. So this whole is at 0 comma something, and again, how I find that something is plugging the 0 into the reduced version, which is here. So if I plugged 0 in here, I would get negative 6 times positive 4 over 3. So that would be negative 24 divided by 3, or negative 8 for my whole. Now that I have crossed that out, I look at my remaining function to figure out the other pieces. The vertical asymptote is what's left in my denominator. It's the line I can't cross at x equals negative 3, and I have two x-intercepts on the top, positive 6 and negative 4. So I have two places that it crosses the x-axis, and here they are. So if I bring this information together, I have a slant asymptote at y equals x minus 5. So it would start down here at negative 5, and I would go up 1 over 1 in both directions. And I'm going to go ahead and make that a dotted line just to make sure that you can see it's clearly a line I can't cross. I have a vertical asymptote at x equals negative 3, so that would be here. I then have some points that are possible. 6, 0 is on my graph. Negative 4, 0 is on my graph. There is a hole at 0, negative 8, so I'm going to put an open dot there. And then to the best of my ability, I'm going to draw a graph that I think is correct. Remember that a rational expression has some symmetry. So my graph is going to start close to the line I can't cross, go through the hole, go through the other x-intercept, and then get again really close to the line I can't cross. So this should probably look a little bit more U-like, but it should look connecting here all the way up. And then because there's symmetry, the other piece of my graph would go along the asymptotes, go through this x-intercept, and then continue parallel in a way to the vertical asymptote. So again, if I drew this just a little bit better, because it's bothering me a little bit, if this is my hole here at 0, negative 8, your graph would look something like this. A little bit strange, but it is correct. Number 5, solve the inequality by finding critical numbers and then checking your intervals on a number line. So the first thing we need to do on this problem is get one side to be 0. So I'm going to subtract this term over here. 3 over x minus 6 minus 2 over 5x minus 2 is less than or equal to 0. And now that they're on one side of your inequality, we need a common denominator. So I need to multiply this piece by 5x minus 2, and I need to multiply this piece here by x minus 6, top and bottom. And when I do that, I would get 3 times 5x minus 2 on the top, minus 2 times x minus 6. Now I have a common denominator of the 5x minus 2 and the x minus 6, and this is still less than or equal to 0. I'm not going to multiply out my denominator, but I am going to multiply out my numerator. And when I do that, I get 15x minus 6 minus 2x plus 12 all over 5x minus 2, and x minus 6 is less than or equal to 0. I don't want to multiply out the bottom because I can see my critical numbers as of now. If I keep combining on the top, I would get 13x plus 6 over 5x minus 2, and x minus 6 is less than or equal to 0. So my critical numbers as of now are x equals 2/5, because if I set that equal to 0, x equals 6 if I set this equal to 0. And if I set my numerator equal to 0, I get a lovely answer of negative 6/13. So if I make my number line down here, my critical numbers would be at positive 6, and that would be an open dot because it's in the denominator. I can never equal the denominator. 2/5 would also be an open dot because it's in the denominator. However, negative 6/13 would be a filled in dot because we have a less than or equal to, and the numerator is a 0, so that is possible. So what we need to do is check our intervals here. And again, you could either plug in numbers or you could do it by signs. It is your choice completely. And I'm going to plug everything into this. So if I think about negative 6/13, I know that negative 1 is less than this term. So if I plug negative 1 in the top, I would get a negative number. If I plugged negative 1 in this piece here, I would get a negative number. And if I plugged negative 1 here, I'd also get a negative number. So negative divided by a positive is a negative number, and a negative is less than 0, so this region works. A number that's between negative 6/13 and 2/5 is the number 0. So if I plug 0 in the top, I get a positive. 0 in this piece is a negative, and 0 in x minus 6 is also a negative. So positive divided by positive is a positive, which is not less than or equal to 0, so that does not work. The number positive 1 is between 2/5 and 6. So if I plug 1 in, I get a positive on the top. 1 down here is a positive, and then 1 here is a negative. Positive divided by a negative total is a negative, which does work here. And lastly, if I plug in a number like 7, if I plug 7 in the numerator, I get a positive. 7 in the denominator, I get a positive. And 7 in this denominator, I get a positive. So that's all positive, which is not true and not less than or equal to 0. So that does not work. So in purple here, my final answer in interval notation would be these two regions that are less than or equal to 0. So that would be from negative infinity to negative 6/13 with a bracket because it is included, union, both of these are not included, so we'd have parenthesis 2/5 to 6. So this would be my final answer in interval notation. Number 6, use the graph of the function to answer the following question about limits. All right, let's see here. So for part A, f of 0 means I want to find the exact y value where the x value is 0. So if I look at the x value of 0, the only place that y exists is at 0 itself. So the point 0, 0 exists on my graph right here. F of 2 means what y value exists at the x value of 2. Well, it looks like I have a vertical asymptote here, so no y value exists here exactly. So this would be does not exist. F of 3, what a y value exists at the x value of 3? Looks like it crosses the x-axis at 0. So my answer for part C is 0 as well. Part D asks, what is the limit as x approaches -1? But notice it does not say a direction, so I need to check both. As you're approaching -1 from the left, it looks like it's going towards positive infinity. As I'm approaching -1 from the right, it looks like it's going towards negative infinity. So because the limit's not the same from both directions, that means the limit does not exist. Part E, the limit as x approaches 0. So from either direction, if I approach from the left, it approaches 0. If I approach from the right, it approaches 0. So the limit is exactly 0 because it's the same from both directions. Part F, the limit as x approaches 2 from the right side. So as my graph approaches 2 from the right, it looks like it's going all the way down towards negative infinity. So it is approaching negative infinity for part F. And finally, part G says the limit as x goes towards infinity. So as the graph keeps going forever towards infinity, what is the y value doing? So as my graph goes this direction, it looks like it's leveling off and approaching this horizontal asymptote at 1. So my graph is getting very close to 1 as x goes to infinity.